All right, students, let us proceed on from where we left last time. So, want to look more about this uh, diagram, which I'm going to call the reaction coordinate diagram, which I've mentioned a couple of times before. Uh, and and just to say that it gives the plot of the free energy, which is the delta G. It's being plotted against the progress of the reaction. It means you're going to have the starting materials as they're going to be proceeding through the various, probably it can involve one intermediate, it can involve two intermediates, and then it proceeds to the product. Yeah. Yeah. Uh, so it shows a hill or a barrier that must I don't know whether this one is looks most, but it should be you. It should be you with a mass that must be overcome for the reactants to form the product. Yeah, and the highest point of this hill is called the transition state, and it gives the most unstable structure that can be formed. Um, so so in a transition state, which are going to abbreviate to TS, the bonds are breaking and forming. Just to give an example, in this case, there is the hydroxyl group. It is attacking, and in this case, it is methyl chloride. Yeah, and this is a reaction which you know. This an SN2 reaction. Uh, the nucleophile is strong, and then the leaving group, which is the halide, is a good leaving group. So this reaction proceeds via, in this case, a five uh, uh, membered. It's like an intermediate. It's not like like one which can be isolated. As I mentioned, a transition state is the most unstable structure. So it means you cannot isolate. Yeah, there should be other structures which are more stable than the transition state. So in this case, in the transition state, it means some bonds are breaking and some other bonds are forming. So in this case, this the developing the bond that is forming, and this the bond which is breaking. Yeah. So maybe later, it may not be in this course, but maybe whoever will be teaching, I think SH 504, I think it's Dr. Nakala, may be showing the orbital of overlap. For example, you're going to see, like in this case, like the bond between carbon and chlorine will be represented as these other bonds are just represented here, and then there is a lobe, and then there is the overlap between between the p orbital of carbon and chlorine. In this case, these are full. Can you see this p orbital? There's a perfect overlap between my carbon and chlorine. Yeah. But when you're going to have like in a transition state, I'm having a case whereby this this orbital is is moving away. So you're going to have a situation whereby that orbital is just it's just touching it. There is no overlap. It's just touching the this p orbital of carbon. Yeah, yeah. So this is a bond which is partially forming or partially breaking, as opposed to the one which I'm showing here, whereby there's the proper overlap. In this case, I'm showing there is a head-on overlap between. In this case, I'm forming a sigma bond between two two p orbitals. There is head-on overlap, so there is a perfect overlap. But as you're moving towards the transition state, then that overlap becomes in such a way that it is partially forming and partially breaking. So the overlap is just uh, overlap is the minimum. So that is what is being represented as my dash bond. Yeah, please know this, that carbon forms 4 bonds. In this case, we're not saying that that carbon forms 5 bonds. In this case, you're going to say at the end of this loop here, this other orbital is actually interacting with your hydroxide. So the p orbital of the oxygen is interacting with this one, and in this other case, still on the other side, the for the same orbital, the chlorine is leaving. But once again, um, uh, when you'll be looking at the synthetic then and more about mechanisms, then I think these things are going to be shown. But for now, I think I will not mention much about it, but it's a very important thing if you really need to understand mechanisms in organic chemistry. Now, there are some four diagrams which I've shown here for the reaction coordinate diagram, whereby there's the delta G being plotted here, and then there is a hill here, yeah? So there is a big hill, and then what you have here is that the starting material uh, have got less energy than the product. So in this case, the product is absorbing the energy. So it's more or less like what? Please note, this is not exothermic and endothermic. This is delta G. So in this case, we'll be talking about hexagonic and endagonic. So this is an endagonic reaction. This is an endagonic reaction. This is an uh, hexagonic reaction. This is also another hexagonic reaction. But in this case, this one has got a very large activation barrier to be overcome. This one has got a small activation barrier to be overcome. Now, uh, there's some terminologies here which are put here. E-act. Oh, it's not AT. This is energy of activation. E-A. It is E-act. Yeah. It is energy of activation. Yeah. I'm sorry for that. It is not AT, but E, energy of activation. Now, energy of activation becomes evident when we'll be talking about kinetics, because uh, there is this reaction which you've dealt with, equilibrium constant, the concentration of the products over the concentration of the reactants, and also the delta G naught under the standard conditions is the delta H under standard conditions minus T delta S. So you're going to see this reaction will just tell you, yes, you're forming a more stable product, but how quickly? So in that case, then the issue about the E-Act is dealt with under kinetics. It's dealt with under kinetics. Kinetics tells you how fast a reaction is taking place. Uh, in other words, for example, this is this said to be a uh, endagonic reaction, and the activation barrier is large. So this will be said to be a slow endagonic reaction. This is a fast endagonic reaction. Fast, it means the activation energy is small, and but still the products are at a higher energy than the starting material. This is an hexagonic. It means that the products are at a lower position than the starting material, but there is a big barrier. So this is a slow hexagonic reaction. This is a fast hexagonic reaction. There's a small barrier, and then the the delta G of the products is lower than the one for the starting material. So it's an hexagonic reaction. Yeah. So we are going to see a new relationship between delta G and the delta H. Yeah, yeah. That involves knowledge of the activation energy. Yeah. So there will be a new term which is going to exclude uh, which is going to exclude this T delta S. Yeah, you're going to see a new terminology, and in that case, then we are not going to have the normal delta G naught. You're going to be coming to a new terminology which are going to call delta G. Can you see that term? There is a line and then there are two. So this is giving you the free energy for the kinetics, yeah, and we are going to see a new relationship with the activation energy. So in this case, now we are starting to talk about kinetics. We are now through with uh, with thermodynamics, yeah. So I think once you are through with everything up to learning about activation energy and other things, then I'll be able to give you problems to solve so that you'll be able to look at. Because currently you'll just be looking at an equation, but if you're given a problem to solve, then you'll be able to see this problem from the different perspectives. So I really hope you've really enjoyed what you've been looking at so far has been thermodynamics. Now we want to look at kinetics proper. Yeah? Okay, so I think we'll just stop there and then we'll start looking at kinetics.